So welcome everyone to the VGP Awards presentation and the Daly Lecture. More than 200 volunteers make our section work. You know who you are, so please accept my sincere thanks for your selfless contributions. Our meeting was organized by Christy Till and Matt Jackson. They received lots of complaints, and so this is the chance to thank them for their hard work in dealing with so many challenges, especially this year. I'd also like to thank the early career representative, Matt Barrickman, who organized the VGP student event. All AGU sections recognize a small number of students for outstanding presentations. This recognition is not possible without a huge effort, an effort organized by Tyrone Rooney. And more than 150 people volunteered their time as judges. Last year, 10 students were recognized. Rebecca DeGraffenreid from the University of Hawaii. How robust are our assumptions in using crystal-hosted melt embayments to estimate magma ascent rates? Alexander Petravkin, University of Innsbruck. OH defects in quartz as petrological indicator and provenance tool. Lucy Tweed, Columbia University, Lamont Doherty Earth Observatory. A tractable approach to coupling the thermodynamics, kinetics, and fluid dynamics of mantle melting. Heather Winslow, University of Nevada, Reno, exploring the role of mafic magmas and the volatile content during the 2011-12 Buyehwe-Cordon-Caye eruption. Stuart Conderas, University of Missouri, Columbia, rheology of bubbly rhyolites and its effects on the emplacement of obsidian dome. Jennifer Kasbaum, Princeton University, assessing eruptive tempo of the Columbia River basalt group and recalibrating Miocene climate records with zircon geochronology. Meng Ga, Yale University, argon constraints on the growth of continental crust and its composition. Francis Borham, University of Bristol, rootless cones and tree root lava, recognizing lava-water interactions remotely. Maximilian van Vack de Vries, University of Minnesota, large volcanic landslides on the southern Patagonian icefield and linkages to glacial retreat. Emily Stewart, Yale University, decarbonation of the subducting slab, observational constraints from the cycladic blue schist unit, Greece. AGU as a union recognizes Earth and space science with union awards and medals. This year, 2 VGP members are recognized with union medals. Don Dingwell from LMU in Munich is receiving the Hess Medal. Marie Edmonds from the University of Cambridge is receiving the Joanne Simpson Medal. VGP has canvassing committees to try and ensure that our science is being considered and recognized. So please do nominate your colleagues and reach out to these committees or me if you need help. People cannot be recognized if they're not nominated. VGP also offers 3 section awards. The Bowen Award was awarded to Brad Hacker from the University of California, Santa Barbara. Professor Hacker's in the field and not able to participate this year, and so the award and the associated lecture will be presented at the fall 2021 meeting. This morning, we do present the VGP Early Career Award. The Kuno Award is presented annually to an early career scientist for outstanding contributions to the fields of volcanology, geochemistry, and petrology. It's named to honor the life and work of Hisashi Kuno, an exceptional volcanologist and petrologist of the mid-20th century. Awardees are no more than 7 years past the completion of their PhD, or the highest terminal degree by the beginning of the year in which the award is presented. And this year's Kuno Award is presented to Claire Buchholz from Caltech, and to deliver the citation, we have Jay Agu from Yale University.
Thank you, Michael. I'm delighted and honored to introduce Claire Buchholz, the recipient of the 2020 Hiroshi Kuno Award. Claire is an igneous petrologist and high-temperature geochemist whose rigorous approach to fundamental problems in magmagenesis builds on the quantitative petrology legacy embodied by Kuno. A key theme of Claire's research is fractional crystallization, arguably the most basic phenomenon in all of igneous petrology. For her PhD work at MIT with Oliver Yagutz, she showed that the alkaline fractionation trend, one of the 3 main igneous fractionation trends, is far more important than previously thought in the petrogenesis of silicic arc rocks. Furthermore, she has constructed novel and elegant oxygen isotope models to trace closed system fractionation, as well as open system processes such as assimilation. Another major theme is fluids and redox state. This was evident early on in Claire's undergraduate work on fluid flow through oxidized schists, and later with her groundbreaking studies of volatile and oxygen fugacity reequilibration in olivine-hosted melt inclusions. Claire is now integrating these themes in dynamic new ways. For example, she is illuminating the geochemical significance of paraluminous magmas in the geologic record, including the long-term evolution of the redox state of metasedimentary source components and the role of crustal melting in the Archean sulfur cycle. Her findings link superficial and deep processes and show the potential of the petrologic record for tracing geochemical cycling in deep time. The spirit of bold creativity is a hallmark of Claire's research, which masterfully integrates field and laboratory observations, experiments, and testable geochemical and thermodynamic models to open up new scientific directions. The breadth and scope of her work are truly remarkable, and we look forward to her future discoveries.
Thank you, Jay. It's truly a great honor to receive this award, and I would like to thank all the people involved in my nomination and also the BGP section. My formal geologic training began at Yale with Jay as an undergraduate, and Jay taught me the importance of making detailed field observations and lab measurements and then rigorously scrutinizing the data. Also, very importantly, Jay showed me the importance of high quality and conscientious mentorship. And my foundation as a geologist is truly owed to him. I would also like to thank the other members of the Yale faculty while I was there, such as Brian Skinner, Mark Brandon, and Dave Evans, for their inspiring classes and endless enthusiasm for geology. In graduate school, I worked closely with both Ollie Agutz and Glenn Gaetani. Ollie and Glenn served as role models for how to simultaneously be creative, but also rigorous in the scientific method. And as a postdoc at Caltech, I had the true pleasure to work with Ed Stolper and John Eiler, both of whom pushed me to think about big problems, but also to never lose sight of the details. I'm lucky to have had all these wonderful mentors. And I've now been an assistant professor at Caltech for 3 years, and I'm blessed to work with colleagues and a community there who believe in me and continually offer support and advice. I would also like to thank my family, beginning with my mother and father, who were unwavering in their support of my education, beginning from when I was a little girl. And they were both doctors and medical researchers, and they imbued their appreciation of science in me. And last, I also especially wish to thank my husband, Devin, for his unending support of my career and our young family, as well as helping me keep things in perspective. And then there are my son, Owen, and my daughter, Margot, and their natural inquisitiveness and their joy of exploring the world inspires me daily to keep searching for the truth while applying the most rigorous standards. Thank you very much.
Congratulations again, Claire. It is with the greatest pleasure that I get to introduce the 2020 Daly Lecture Maud Boyer from the Laboratoire Magma et Volcan at the Université Clermont-Auvergne. Dr. Boyer is an isotope geochemist and cosmochemist. She develops state-of-the-art methods to make high-precision isotopic measurements that provide quantitative insights into the chronology of early solar system processes. This includes the formation of the Earth and our Moon, to compare our early evolution with that of other rocky objects in our solar system, and to constrain the dynamics and structure of Earth's mantle. With new, very demanding and time-consuming high-precision samarium neodymium data for Earth and meteorites, she provided evidence for the existence of the early formation of an enriched and unsampled reservoir in the deep mantle. The results of her analyses have fundamental implications for models of Earth's compositional structure, questioning the chondrite analog compositional model. There are also implications for the timing of global differentiation of Earth's Moon and Mars. Maud Boyer also contributed to the discovery of rocks on Earth with an age as old as 4.4 billion years. More recently, she pioneered the analyses of lanthanum and cerium isotopes in oceanic island basalts. She was able to eliminate recycled pelagic sediments as the cause for enriched mantle 1 components in Gough Island. And she determined that cerium anomalies in the Marianas Arc magmas come from recycled trench sediments through active subduction. So please welcome and congratulate Dr. Maud Boyer, the 2020 Daly Lecturer.
I'm very pleased to give this presentation today, and of course, I'm very honored to receive this award. The title of my presentation is Terrestrial Magma Ocean Geochemical Constraint. I have started to work on this subject during my PhD with Francis Alvarez and Neil Bischoff-Toft in Lyon. The main goal was to develop the measurement of the short-lived 146 samarium-142 neodymium systematics. This was the beginning of the study of this system. In 15 years, results obtained with the systematics have provided strong constraint on the early evolution of the silicate Earth. I would like to show you today that the magma ocean stage has been recorded by several isotope systematics, and we can use this data to better constrain and date this event. I really want to thank all the people who have worked with me on this subject. So magma oceans are common in the planetary evolution. Firstly, shortly after the beginning of solar system accretion in small planetesimals, the melting is induced by the presence of short-lived radionuclides, such as 26 aluminum, whereas after a few million years, both gravitational energy liberated by accretion and core segregation will enhance significantly the temperature. Then, violent collision occurred in the final stage of accretion. For the Earth, the last important event is the giant impact forming the Moon. We expect that large collision may have changed the bulk composition of the planetary bodies and produce large melting events. My presentation is organized in 4 main parts. I'm going to start with evidence for the existence of magma ocean stage from extraterrestrial samples. Then we will go back to Earth. 2 types of samples are mainly studied to track the early Earth mantle evolution. Very old samples formed in the Archean and Hadean period, and volcanic samples of deep mantle origin. In this second case, they will be useful if primitive reservoirs have been preserved from mantle convection over more than 4.5 billion years. The last point concerns the timing. How can we access to the chronology? And in the last part of my presentation, I will present some recent results that are being debated to show that there is still a lot of work to be done. So the magma ocean is a lunar concept. Wood et al. In 1970 were the first to suggest that anorthotic rocks, so these white rocks forming the lunar island, could be remnant of the earliest lunar crust formed by crystal fractionation and plagioclase flotation during the crystallization of the lunar magma ocean. The opposite Aortian anomaly observed between anorthosite here and basalt sample collected in lunar Maria is explained by the early crystallization of lunar crust. Aortian is compatible in plagioclase, then the Moon's interior is depleted in this element once the plagioclase crystallizes. So the crystallization of the lunar magma ocean is predicted to produce distinct chemical reservoirs. Mafic silicate crystallized from initially extensively molten moon and subsequently sank into the lunar mantle. After some 70 to 80% crystallization, the plagioclase began to crystallize. And from what was by then a dense iron-rich differentiated magma, causing the plagioclase to float to form this thick lunar crust. Further crystallization caused the residual liquid that is strongly enriched in incompatible elements. That was given the name creep, that is enriched in potassium, rare earth element, and phosphorus. The timing of metal silicate segregation on small planetary bodies is obtained from the study of magmatic iron meteorites. This sample represents the core of small-sized objects of few tens of kilometers in diameter. So here, age are presented using the 182 hafnium, 182 tungsten short-life systematics. So the small variation in 182 tungsten measured in magnetic iron meteorite from different groups are converted in age. So here it's a timing interval from the beginning of solar system accretion, the condensation of the first solid, the calcium aluminium rich inclusion. So core formation occur over an interval of 1 million years here after the beginning of solar system formation, and these ages are well explained by the post-accretional heating, internal heating by 26 aluminium decay. When we look the silicate part of asteroid, we reach the same conclusion. So here are presented the oxygen isotopic composition measured in two groups of samples, the howardite, diagenite, and eucrite in red. So here, which are thought to sample the asteroid 4D star and angrite, so basaltic rock, here in blue. The oxygen isotopic composition measured in different types of achondrite demonstrate that this meteorite suite formed from an homogeneous reservoir that subsequently fractionated by mass-dependent fractionation, mass-dependent processes. The HED and the angrite parent body underwent global-scale oxygen isotope homogenization event. The melting process occurred very early in solar system history and is also induced by the decay of 26 aluminium. So why is it so difficult to track the early Earth silicate history? So the main reason is because our planet is young. It's an active planet and the Earth's surface is young. 80% of the age are younger than 200 million years. Of course, the ocean represents 2/3 of the Earth's surface. Very old blocks of continental crust are scarce, and here are represented the main location of terrain with age older than 3.6 billion years. So samples are scarce, but terrain have been identified in Australia, in South Africa, in Antarctica, in China, and several belts in the North Atlantic Craton, in Greenland, and Canada. So the contrast is striking when we compare with the Moon. For the Moon, 80% of ages are older than 4 billion years. This time depth diagram presents availability of data for constraining geodynamic relationship for the Earth. The size here of the data point reflects abundance of available data. So today we have a ton of data with many samples available for measurement, and geophysical data provide a very good knowledge of the Earth's interior. However, the rest of the diagram is fundamentally devoid of observational data. So in order to better constrain the early Earth evolution, we analyze very old samples and samples that may have a very deep origin and that could be able to give information on early form reservoir preserved from mantle convection since their formation. So isotope geochemistry, and more specifically short and long-lived radiometric systems, are very powerful to track early silicate differentiation events. I will present data for the 146 samarium, 142 neodymium short-lived systematics. So here with a half-life of 103 million years. So this system is alive during the first 500 million years of solar system history, and then 142 neodymium variations are related to ADN magnetic processes. And among the long-lived radiometric systems, these two systems are preferred because they are particularly robust during metamorphic processes, and all the old terrestrial samples have known successive metamorphic events, and we need to measure isotope systems that have not been disturbed. So result from the 146 samarium 142 neodymium systematics obtained on sample coming from southwest Greenland, and most of them from the Isua supracrystal belt, it is shown here, are presented on this diagram. So the precision commonly obtained on the measurement on the 142-144 neodymium ratio is about 5 ppm, minus plus 5 ppm. It is clear that these samples coming from different units have excess in 142 neodymium relative to the terrestrial standard value here at 0, which is similar to the modern accessible mantle. So to develop excess in 142 neodymium, this means that the source of these samples has known parent-daughter fractionation during the ADN. So the mantle source has high samarium neodymium ratio, and this isotope signature is a very strong argument for a major early silicate event in the Earth mantle. This slide presents results from long-life samarium neodymium and lutetium hafnium systematics obtained on the same sample, so on Isua on fibolite collected on the northern part of the belt. For the samarium systematic, so it's this diagram, we can see two groups of samples. So one group forms an isochrone with an age of 4.7 billion years, which is consistent with the minimum uranium late ages measured on zircon from cross-cutting tonalites, and a few samples here in black yield a younger age of 2.9 billion years, and these samples are poorer in neodymium and systematics has been disturbed during a later metamorphic event. For the lutetium hafnium systematics, it seems that the system is more robust to post-emplacement modification because only 2 samples fall off the 3.7 billion years isochrone. So using this isochrone method, we can define the initial isotopic composition of the mantle source. So the initial epsilon 143 neodymium is positive with a value of plus 1.4, and this result is consistent with positive anomalies in 142 neodymium measured in these samples. The initial epsilon hafnium value is negative with a value of minus 1.4. So to develop this isotopic signature, the mantle source has evolved with low lutetium hafnium ratio. The amplitude of the 142 neodymium anomaly variation, so this is also true for variation measured in long-life systematics, depend on 2 parameters, the age and the magnitude of the parent-daughter fractionation. These 2 parameters are shown on this plot. You can follow the 142 neodymium evolution for 2 timing, so at the beginning of solar system history and 200 million years later. The final anomaly will be higher for a reservoir fractionated earlier, so it's shown by this curve. Why? Because the parent isotope, the 146 samarium, decay quickly over time. So the second parameter is illustrated by this different curve for a single differentiation event. So the more the samarium neodymium ratio is modified, so for example here, the more the anomaly is important. So using this notation, the 142 neodymium is expressed relative to the primitive mantle value, which is assumed to be chondritic for this refractory lithophile element. So with a few ppm of precision, it is very difficult to identify silicate event produced after 300 million years. The fractionation between samarium and neodymium, which are 2 elements with similar behavior, is always very small. So to give you an idea, this ratio is about 0.25 in the source of mob samples and can reach 0.3 or 0.35 in pyroxene and garnet. So it is extremely clear, looking at the 142 neodymium compilation, that variations are measured in the oldest terrestrial sample, and the maximum deviation is about 20 ppm in the samples, the Isua samples coming from southwestern part of Greenland. In the modern terrestrial samples, the 142 signature is much less variable. The mantle has been homogenized through time by mantle convection, but the mantle was strongly heterogeneous until 3.5 billion years. The Samarium neodymium systematics is extremely powerful because we have two unknowns, but we can combine results from the two systematics, the short life system and the long life systematics. And we can resolve the two equations. The age of the fractionation event can be calculated assuming a simple two-stage model. So the fractionation was a single event. And we have a second assumption in this calculation. The source has not been modified between the first fractionation event during the ADN and the age of rock crystallization. So here we discuss about Aortian Symptoms. So I present here a graph published by Moreno et al. Reporting data on samples from different locations, Canada, Greenland, South Africa, and Australia. Using this compilation, they obtained a correlation, and most of these samples plot along a 4.4 billion years old isochrone that suggests the age of the terrestrial magma ocean is 4.4 billion years. So when we look at the 142 neodymium anomalies measuring samples from different planetary bodies, we see that the amplitude of the anomaly is not correlated with the size of the object. Here, the scale is restricted relative to the Earth diameter. So for the asteroid 4B star, measured samples are mostly eucrite, both basaltic eucrite and cumulate eucrite. They have the largest 142 neodymium anomaly. As I have shown in the previous slide, the eucrite parent body has known a magma ocean stage very early in the solar system history, and the largest anomaly here are measured in pyroxene that have very high samarium neodymium ratio. So large 142 neodymium anomalies have also been measured on Martian meteorites. They are all bulk sample measurements. And when we try to calculate an age using the samarium neodymium systematics, we obtain a differentiation event around 40 million years. Other isotope systems suggest that the magma ocean stage on Mars occurred earlier during the first 10 million years. For the moon now, we have samples, both lunar meteorites and Apollo samples. It is clear that the amplitude of the 1 anomaly is relatively small. We have small difference between the samples, and the highest variation are measured on samples from the lunar crust. They are composed mostly of plagioclase with very low samarium neodymium ratio. The younger samples coming from the lunar mantle have very small excess here of 142 neodymium, and they are measured in basalt, so low and high titanium basalt, and we have small deficit for the crude basalt. Now, if we add on this graph the 142 neodymium data measured on Archean sample, we note that excesses measured on the moon and on the Earth are in the same range. The maximum 142 neodymium excess reached 20 ppm in both lunar and terrestrial samples. So the amplitude of the 142 neodymium variation gives us first-order information on the timing of the silicate differentiation event. For the Earth-Moon system, the silicate differentiation is relatively young, much younger than the event which has produced large chemical heterogeneities in the Martian mantle. So now more information about the differentiation of the silicate mantle is obtained when looking at the mineral melt partition coefficient of upper and lower mantle phases. So we know that the mineralogy changes with depth. In the upper part of the mantle, in low pressure environment, the mantle is composed of olivine, pyroxene, and garnet. Many studies have measured the partition coefficient of trace elements in these minerals. And at high pressure, it is a mixture of ferropericlase, bitumenite, and calcium peroxide. Of course, it is much more difficult to measure the partition coefficient for trace elements in high pressure experiments, but this data exists in the literature. So here we plotted the mineral melt partition coefficient for upper mantle minerals. Parent daughter elements, so for samarium, neodymium, and lutetium hafnium systematics, are incompatible. The partition coefficients are lower than 1, except lutetium and garnet, which is compatible. Samarium and neodymium are both rare earth elements, and they share very similar behavior during magmatic processes. So a partial melting event produces a residue here that is depleted in incompatible elements, and a complementary reservoir, so liquid that is enriched in incompatible elements. So if we consider the silicate terrestrial reservoir, here it's depleted non-mantle, and here it's the continental crust. So these two reservoirs have very different rare earth element pattern because the enriched reservoir and the residue have opposite pattern. So the crust with a low samarium neodymium ratio and the depleted non-mantle with a high samarium neodymium ratio, they will evolve with different isotope signature with time. But it is extremely important to note that in both systematics, daughter elements shown in red, so hafnium and neodymium, are more incompatible than parent elements shown in blue. This behavior explains the overall positive correlation observed for hafnium and neodymium isotope in modern terrestrial mantle called the mantle array. So the positive correlation between neodymium and hafnium isotopes in terrestrial samples attest to congruent low-pressure behavior of lutetium hafnium and samarium neodymium ratio during igneous differentiation processes. We say also that we have a coupled evolution for these two systematics. But the picture is different if we consider now the mineral from the lower mantle. So in calcium peroxide, so here in black, trace elements are compatible or close to 1 for hafnium. But the bitumenite pattern, here in red, is completely different. The slope for hafnium lutetium is that means that the samarium neodymium and lutetium hafnium systematics can be decoupled when deep mantle mineral phases are involved. Bitumenite is the only abundant mineral that preferentially concentrates hafnium relative to lutetium. The bulk partition coefficient calculated for a mixture of bitumenite, ferropericlase, and calcium peroxide, reproducing estimate for the lower mantle, is presented in this diagram. We note that samarium, neodymium, and lutetium hafnium are decoupled when the bitumenite proportion, so this line, exceeds 77%. Then the bulk partition coefficient for lutetium becomes smaller than that of hafnium. And then the samarium, neodymium, and lutetium ratio are inversely fractionated during melting or crystallization. So lutetium hafnium and samarium neodymium fractionation during the crystallization of a deep magma ocean is shown in this second figure. Compositions are represented for 5, 10, 20, 30, 40, and 50% of crystallization. The composition of both cumulate and residual liquid are on these two parts, these two yellow parts of this diagram. So the composition of both cumulate and residual net are calculated at each step using a batch crystallization model. So for one line, we have a constant mineralogy, and a calculation has been made for a constant proportion of ferropericles, 16%, and variable proportion of calcium perovskite from 2 to 7%, and bridgemanite from 77 to 82%. So when the proportion of bridgemanite exceeds 77%, both residual liquids and cumulate plot in this yellow field, the residual liquid in the upper left and the cumulate in this quadrant. The OIB-MOG correlation, so the Monte array, is represented to show the positive trend commonly observed from ocean island and mid-ocean ridge patterns. So the crystallization of a deep magma ocean when the bridgemanite proportion exceeds 77% can be identified because the two systems will be decoupled. So how to constrain the parent-daughter ratio in the source? So in the case of ISUA, we have three important information: the measure 142 neodymium value, and using the isochrone method, we have an initial epsilon 143 neodymium and an initial epsilon hafnium. These values are reported here, and we can obtain the parent-daughter ratio of the mantle source. So the samarium neodymium ratio is higher than the primitive mantle, and the lutetium ratio is lower than the primitive mantle value. So we are located in this field. Here we consider that the source of ISUA and fibrillite has recorded a deep ocean event. To explain the decoupling between the samarium neodymium and the lutetium hafnium isotope system in ISUA and fibrillite, we propose a model consisting of deep-seated mantle source composed largely of bridgemanite and a small fraction of calcium perovskite. So in the second part of this presentation, I will show you results obtained on chromatides. So chromatides are ultramafic volcanic rocks found mainly in Archean greenstone belt. There is strong petrological evidence that they are derived from a deep mantle. As such, they are able to give us valuable information on part of the early mantle that is rarely accessible. We have known for a long time that these chromatides have mildly radiogenic initial neodymium and hafnium isotopic composition, indicative of very old incompatible element depletion events in the mantle. So here I present new results on the 146 samarium 142 neodymium isotope systematic of Barberton chromatite from the chromatic formation and surrounding sedimentary rocks, so mudstone and sandstone from the fig tree woods and buck pictures from the Kronberg formation. So this formation was sampled during an ICDP drilling project that was carried out a few years ago. All these samples were analyzed previously for samarium, neodymium, and lutetium hafnium systematics, so the long-life samarium neodymium systematics, so in Bischertoff et al. And Garçon et al. Previous results published during the past few years obtained on both Barberton chromatite, but also on Skapenburg chromatite, which are located a few kilometers away, have shown that the two lutetium hafnium and samarium neodymium systematics were decoupled in the mantle source. Then we have decided to measure the 146 samarium 142 neodymium systematics on few samples already analyzed by Jan Bischertoff, and 142 neodymium measurement have been already published for Skapenburg Chromatides. So a few years ago, they have been measured by Igor Petrov. So all the results measured on chromatides are presented in this slide. In the left diagram, results from the literature. The first deficit in 142 were identified in Skapenburg chromatides. Sample analyzed by Catherine Schneider here show also small deficit in 142 neodymium. The samples are metatolerites of the chromatic formation and 2 metachromatides from the Daly-Lecture remnant. Other samples have no anomaly, so value here at 0. Among these samples, some of them are also from Barberton. So our new results are presented on this diagram. Individual measurements and the mean value is represented with symbols, so the mean value with the thick line. So chromatite sample have 142 neodymium deficit, ranging from -2 to -8. Values are barely resolved from the terrestrial standard at 0, but the entire population of the sample provide negative 142 neodymium value, and the deficit is very close to the deficit measured for Skapenburg chromatides. So we have measured in the same study, so modern basalt from Hawaii, the value is at 0. And for the sediment, so here in blue, the sediment show a larger variability in 142 neodymium. So considering the average of all measurements performed for each sediment, we note, however, that 80% of the analyzed sample have negative mu 142 neodymium. So in this diagram, all the samples for which we have both hafnium-samarium ratio and 142 neodymium measurements are represented. And it is very interesting because we note a positive correlation in this diagram. So analyzed CDP, Barberton, and Skapenburg chromatides share very similar geochemical characteristics. They are all aluminum depleted. They display a similar rare-earth element pattern with depletion in heavy rare-earth element relative to middle rare-earth element. And they have low hafnium-samarium ratio compared to the primitive mantle value. So the primitive mantle value is here at 0.7. We can see here that the 4 aluminum depleted chromatides from the chromatic formation, so here in white, with no anomaly in 142, are closer to the hafnium-samarium value of the primitive mantle. So one sample, this one, fall off this correlation, and several geochemical evidences support a modification of its composition during metamorphism or hydrothermal alteration. So mu 142 neodymium and initial ratio expressed in epsilon, so for 143 and hafnium, are resumed in this table. So for ICDP, Barberton, chromatite, and Skapenburg chromatides, we have small deficit in 142 neodymium, so the source must have been characterized by low samarium neodymium ratio and formed during the ADN when the extant radioactivity was still alive. So initial epsilon 143 neodymium calculated from the regression, so considering only sample measured for 142 neodymium, give a value of 0, but Bischoff et al. Discussed this in more detail. They obtain a slightly positive value of +2 if they consider all the samples, and they obtain a slightly negative value when they measure only separated very pure pyroxene. So the message is not clear looking only the long-life samarium neodymium systematics. The lutetium hafnium systematics give more consistent information. So considering clinopyroxene or bulk work measurements, the initial value is always positive, so here a value at +2. For Skapenborn Chromatides, so we have a small deficit in 142, and this contrasts with the positive epsilon 143 neodymium and positive epsilon hafnium calculated at 3 at the age of these samples. So these results show that the mental source of these chromatides has experienced successive differentiation events early in history. To obtain the entire history of mental processes requires coupling of results obtained from several isotope systems. So it seems that the samarium-neodymium ratio has been modified between the first fractionation event during the ADN and the age of crystallization of these chromatides. So here we identify clearly a second melting event which has weights both parent-daughter ratios, samarium-neodymium and lutetium hafnium. So if we resume the two systems were decoupled. So this is a sketch of trace element pattern of a source that produce low samarium-neodymium and high lutetium hafnium ratio. So Bischoff et al. Discuss two scenarios in their paper to have a source with this geochemical characteristic. It will be produced by the recycling of deep sea sediment in the source of Barberton chromatides, or we identify here, in the mental source, the crystallization of a deep magma ocean. Of course, the sediment that have been potentially recycled into the mental source are not known. However, using the sediment found in the Barberton area, we have a first-order idea of the diversity of sediments. So, based on the major and trace element composition of the sediment, Marion Garçon identified 3 groups of sediments, and we have also chairs. So, the red line here and title mixing represent a potential pile of sediments subducted during the Archean. Proportions are defined from the Barb 345 drill core lithology. So our calculations show that the 142, 143 neodymium and hafnium isotope signature, but also the hafnium-samarium neodymium ratio, cannot be produced by recycling of crystal material using sediments similar to those sampled in the Barberton area. So only chairs, here in blue, have the white trace element characteristic with very low hafnium-samarium ratio and very highly radiogenic hafnium isotopic signature. But the concentrations are very low, and the required quantity of chairs in the mental source is not realistic if we try to do the calculation. So the modeling of the studied chromatidic source composition requires a crust-chair ratio of 40/60, which will correspond to an impressive thickness of 15 kilometers of chairs accumulated on top of 10 kilometers of oceanic crust. So we propose instead that the isotope signature reflect the crystallization of a deep magma ocean. So this idea of crystal liquid fractionation in an early magma ocean is discussed in this paper for Skapenborn chromatides. So we present here the graph previously described that shows the evolution of the parent-daughter ratio for samarium-neodymium and lutetium hafnium systematics during the crystallization of a deep magma ocean. So for each line, we have a constant assemblage of bridgemanite and calcium perovskite and ferropericlase, and we modify this proportion, so with 2% of calcium perovskite to 7% of calcium perovskite. So samarium-neodymium ratio calculated for the chromatic source can be estimated using this data, so the short-life systematics, and by assuming an age for the magma ocean crystallization. So the model must explain data obtained from the three isotope systems, so the two short and long life samarium neodymium system and the lutetium hafnium, as well as parent daughter and hafnium samarium ratio measuring the chromatides. So the preferred model is an assemblage shown here with the symbol 2, with 76% of bridgemanite, 60% of ferropericlase, and 5% of calcium perovskite. And we reach this value at 30% of crystallization. So this is clearly a signature of the residual liquid with the composition shown here. Then a melt depletion must have occurred to raise the samarium, neodymium, and the lutetium ratio after the extinction of the 146 samarium. So we need that to explain the decoupled signature of the short-life samarium neodymium systematics and the long-life samarium neodymium and lutetium hafnium systematics in this samples. So it is represented by the symbol 3, and this is a depletion event with an age of 4.1 billion years. Then we need to modify the source and to produce liquid with this composition, so that are measured chromatides. And for that, so the stage 4, we have a decompression melting considering 30% of partial melting of a source made up of 55% olivine and 45% of majorite, which correspond to the mineralogy of the deepest part of the Upper Mountain. So Skapenburn, chromatides, and samples from chromatids, so in green and red, share similar low samarium, neodymium, and lutetium hafnium ratio. So for this sample, the well-trodden chromatides, they have no 142 neodymium anomaly, and they are very different parent-daughter ratio. That means that this sample have known a very different evolution. So this graph presents the isotopic evolution. So for epsilon 143 in black, epsilon hafnium in gray, and the 142 neodymium. So the scale is here on the right part of the graph. So the evolution to time from the start of the solar system formation to the age of crystallization of the Baderton chromatid. So initial epsilon 143 neodymium and epsilon hafnium calculated at the age of crystallization are represented by the star and the circle. And the value in red corresponds to the initial value calculated from the isochron method. So the model will reproduce the negative 142 neodymium value and the positive epsilon hafnium at the age of crystallization. And we obtain a slightly negative value for the epsilon 143, which is in agreement with the value recorded by the clinopyroxene separate and the near zero value if you consider the bulk samples. So because we do not know the exact timing of the different events and the composition of the different reservoirs involved in the isotopic model described in the previous slide, we perform a Monte Carlo simulation assuming variable input parameter at each stage, so for the 4 different stages, so to test the robustness and the sensitivity of the model. So we can note that the Monte Carlo simulation reproduced perfectly the range of samarium, neodymium, and lutetium hafnium ratio and the hafnium samarium ratio. However, the model initial neodymium and hafnium isotopic composition are within the range of those measured in the chromatides, but are under constraint given the wide range of input parameters we use for each stage in the Monte Carlo simulation. But more importantly, we perform several other simulations involving melting events only in the upper mountain, and none of them were successful in reproducing the decoupled neodymium-hafnium isotopic signature of the studied chromatides. So the correlation observed between 142 neodymium and hafnium-samarium ratio in chromatides suggests that the fractionation of hafnium from samarium occur almost entirely during an early event. So only the crystallization of deep mantle phases can fractionate the high field strength element relative to raw earth element and produce anomaly, so in zirconium and hafnium. Okay. So here is the calculation for two reservoirs, the cumulate here and the residual liquid. And we can note that the anomaly in high field strength element remains relatively weak in the residual liquid in comparison to the cumulate. Hence, the trace element pattern of the studied chromatide should not record a strong magma ocean signature. Anomaly in high field strength element can also be observed using the zirconium anomaly. So here the zirconium anomaly is calculated relative to neodymium and samarium. And we note that the zirconium anomaly are high in chromatid drill core and scapen-bone chromatides. And zirconium anomaly are weaker in the welter-Weden samples, so between 0.8 and 0.9. in good agreement with their higher hafnium-samarium ratio and the absence of resolved 142 neodymium anomaly in these samples. So two papers were recently published. They present results on stable isotope fractionation measured in chromatides and argue for the crystallization of an early terrestrial magma ocean, but they identified the signature in well-tethered chromatides. So the first paper is published by Byerly et al. Present oxygen isotope composition, and they note that the composition of fresh olivine are lighter than those obtained from modern mantle-derived volcanic rocks. So a second study, Anselm and collaborators have measured the calcium isotope composition in chromatides from several locations. The olivine cumulate from the Welter-Weden formation in the Baberden-Greenstone belt here, and one cumulate sample from the Boston Creek in the Abitibi-Greenstone belt are enriched in the heavy calcium isotopes compared to the rest of the chromatides. In this paper, they explore the different processes that could produce this variation, and the preferred scenario is that the enrichment in the heavier calcium isotope of the Welter-Weden chromatide originated from crystallization of an early terrestrial magma ocean. We note here that never the sample of chromatide, so here, nor the sample from scapen-bone here have a difference in calcium isotopes. So age estimate for the crystallization of the lunar magma ocean compared to the oldest terrestrial record are resumed on this slide. So model age for the crystallization of the lunar magma ocean and absolute age measured on anorthosite, so sample from the crust, are all around 4.35 billion years. And now, if we look at the oldest Earth record, we have the same timing if we consider the age measured on zircon from Jack Hills, or the result from the 146 samarium 142 neodymium systematics measured on sample from the Neolithic supracrystal belt. So if we look here, the two isochrones, so with the short life 146 samarium 142 neodymium systematics, we can see that both terrestrial samples, so here in blue, and lunar samples define regression with similar slope, and we are around 4.4 and 4.35 billion years. So it is clear that we have no record of the first 150 million years of the solar system history for both the Earth and the Moon system. But other short-life systematics suggest that early form chemical heterogeneity may have been preserved in the Earth mantle despite an active mantle convection. So here I show you results for two different systematics: iodine xenon, which is alive during the first 100 million years, and hafnium tungsten systematics with a slightly shorter half-life. So variation have been measured for these two systems. Here we have a different composition for the Morb source and the Iceland mantle source. And small negative 142 neodymium anomaly have been measured in few hotspots. So here in Hawaii in green and Samoa in blue. So it seems that the preservation of early form heterogeneity means that the Earth mantle was never mixed to the point of homogenization. So the giant impact forming the Moon did not homogenize the whole terrestrial mantle. But a new paper published last year in GPL by Rizzo et al. Suggests instead that the anomaly in 182 tungsten could reflect a core mantle exchange. So in this case, the role of the core may have been underestimated, especially for siderophile elements. So I can resume my presentation in 4 main points. First, the couple measurement of the samarium, neodymium, and lutetium hafnium systematics is a powerful tool to identify the crystallization of a deep magma ocean. So the samarium, neodymium, and lutetium hafnium fractionate in opposite direction where the bridge-mantle proportion in the lower mantle is higher than 77%. Geochemical signature produced during the crystallization of a deep magma ocean, so both in cumulate and in residual liquid, have been recorded in samples from different locations. So here is one phygolite. You can see this beautiful pilolava and chromatide from South Africa. Fractionation ages calculated from combined samarium neodymium, the short life and the long life systematics on Archean sample are mostly between 4.36 to 4.4 billion years, and we have the same age range if we consider sample from the lunar crust and differentiation of the lunar mantle, so suggesting a crystallization of the terrestrial magma ocean shortly following the giant impact from the Moon. This impact could have been so energetic that it could have mixed and homogenized the Earth's mantle. However, this view appears to be inconsistent with geochemical studies that suggest that the Earth mantle was not mixed by the impact. So more work is needed here to better constrain the scenario of the giant impact forming the Moon. I stop here. My presentation is done. So thank you very much for your attention.
Maud Boyer, thank you so much for the inspiring talk on how we can use precise isotope measurements to provide new insights into the early Earth and the important processes that shape the Earth. And congratulations again on being selected as the Daly Lecturer. My name is Michael Manga, and I'm the current president of the Volcanology, Geochemistry, and Petrology section of AGU, VGP. And joining me today is Dominique Weiss from the University of British Columbia, the VGP president-elect. and we're going to be serving as moderators. Please go ahead and put your questions in the question and answer box. And we may be having a few little challenges with our internet connection to France and with France. And so we will do the best we can to try and preserve this connection. So to begin, Dominique, would you like to ask the first question?
Yes, my first question is, obviously, as a geochemist, we're always concerned about having very precise measurements. And these 142 neodymium measurements are very, very demanding. So Maud, can you tell us a little more? What does it take to have a good number? And then how do you see this being easier in the future? And I think we lost Maud. Oh, there she is. No, we lost Maud.
Well, Dominique, you and I can have a short little conversation.
Yes.
The interpretation of the geochemical data from the Chromatides seems to be quite controversial, whether it's a sediment signal or, as she proposed, from deeper earth processes. The answer to that question is obviously important, because if we see a signature of subducted sediments, that confirms that plate tectonics was in operation during the early Earth. Is there a unique way to distinguish between sediment subduction and differentiation in the deep Earth?
Unique might not exist, but well, my understanding, and I'll be a little facetious here, is that anything related to chromatides has been controversial. Mm-hmm. There are geochemical ways to distinguish subductions besides the neodymium and the hafnium, but nothing is a magic wand. And what is also interesting is a recent work that show coupling between tungsten and helium isotopes, but not coupled with any other radiogenic, like long-lived this time, neodymium or hafnium isotopic or strontium signature. So my conclusion is that, and that's related to the question to Maud, is that we need instruments that are more sensitive in order to have a better resolution in the analysis and in order to be able to analyze low-level samples.
And by better precision, does this mean 1 order of magnitude, factor of 2, 2 orders of magnitude?
Yes, but that's not, it's not easy, because if one looks at the early work of Maud, not the early work, but the work she did establishing the 142 anomalies, basically takes 24 hours to have a good analysis, and the error on the analysis is almost limit. The difference between the various samples is at the limit of what the instrument can accomplish. So we would need another order of magnitude, but this is very tricky. So a comment to the audience: we don't seem to be able to recover Maud. So would you mind, if you have any questions, to put them in the questions and answer, or questions or comments, so that we can forward them to her? I don't see anything besides Michael and I. It would be nice for Maud to know that people have heard her and have a few questions.
So while we're waiting, Dominique, there's something she pointed out that we do not have a rock record from the Earth and the Moon of the first 150 million years. Such an important time period in the evolution of our planet and our moon. Is there a prospect for recovering information from that time period? Or will it be forever unknown?
I see Maud. Oops, she was there and she disappeared again. It's very difficult to. There are probably still rocks to be found somewhere in remote areas, but there was so much activity with meteorites bombardment, and it was a very aggressive time period in terms of external impacts and things like that. Also, the planet Earth, because of the atmosphere, has been mostly reworked, so it's very tricky to find any good record.
Right. And I understand Maud is still not with us.
She came back and disappeared. And there are a few questions by Sarah Stewart and Val. Thank you.
And then another excellent question about whether the bulk Earth is chondritic or not.
Yeah, that was my second question. The work for Maud, the early work for Maud on the 142 was defining for that. And when I teach isotope geology, I usually, which I do on a regular basis, I usually finish the class by saying, and I'm going to teach you a lecture where I'm going to demolish everything I've been talking about before. And that's the work about the Earth potentially not being chondritic or having a hidden reservoir somewhere.
Great. So now the questions are coming in.
Yeah. Other questions, please.
And so Anne Davai is asking if only 2,000 kilometers of the mantle was melted by the moon impact. Whoops, the questions are popping up. Could the heterogeneities we see today be coming from incomplete mixing between the deep mantle and that 2,000 kilometers? A similar question, in fact, to what Sarah Stewart asks about the sensitivity of the results to assuming a 2,000 kilometer deep magma ocean.
We have Maud.
Maud, welcome back. It's great to see you from France. Maybe we were missing audio. But to summarize, two questions from Sarah Stewart and Anne Davai is really, how sensitive are the conclusions and results to using a partial magma ocean, a 2,000 kilometer deep magma ocean?
Yeah, well, we'll have to ask that question to Maud, I guess. Maud,
because I certainly do not know that.
Me neither. Yeah, she keeps coming in and out, so that's not going to work. We'll copy the questions and we'll forward to her. Any other comments or questions that we can relate to Maud? There she is.
Welcome back. Okay, let's hope this works now.
Okay.
And
can you hear me?
Yes, perfectly.
Yes.
So Dominique, how about we go back to Sarah Stewart and Val Finlayson's question, and then we can go back to the measurement. And so we have a couple of questions about how sensitive your conclusions are, Maud, to assuming a 2,000 kilometer deep magma ocean. And for those who are asking about will the video be available later, yes, these talks have been pre-recorded, and so you can watch them after the session is over. Dominique, while we're waiting, to go back to our earlier discussion, is there a smoking gun of sediment subduction? Is there one single measurement that could only have an origin from sediment recycling?
Well, people think there's a smoking gun, and then you do more analysis and you see that it doesn't work. Like some people thought that thallium isotopes, because they are fractionated in by iron manganese nodules, could be a signature. It doesn't, but it doesn't work. It's that I personally don't think there is a smoking gun for subduction. There is also the light elements that are fractionated into the subduction zone, like oxygen isotopes and boron. But again, this is controversial, and it's very difficult to keep the signal back in time. But that's my perspective. Both might disagree. Maud, can you hear us? Maybe you could just speak without putting the camera. That might work.
So I close the camera.
Yeah, that works.
The sound is very good. So let's hope the sound is working, and thank you again for the lecture, and congratulations on being chosen as the lecturer. A couple questions are asking about how sensitive your conclusions are to the assumed depth of the magma ocean.
I think what it's important to understand from this conclusion is that we know that we have a deep magma ocean. So in fact, I cannot constrain the depth of the magma ocean. But what we can be sure is that we have the mineralogy. It's not pure bridgemanite, because this will be seen using the lutetium hafnium, because the fractionation will be extremely important. But we know that it's a mixture of bridgemanite and calcium perovskite. So it's probably not at the core mantle boundary, but we think that it can be. But I have no constraint on the depth of the magma ocean.
Could it have been a complete magma ocean?
I would say yes. The difficulty is to know if it's the magma ocean that forms the moon, or if maybe we have several magma oceans on Earth. But yes, it's possible that we had a complete magma ocean, yeah.
At the beginning of this session, we had a discussion about the importance of being able to make such high precision measurements. And you highlighted this in your presentation as well. What are the prospects for being able to make even better measurements and the new insights that could be enabled by such measurements?
Yeah, I think that if we want to increase the precision, it will depend on the instrument. It cannot be an improvement by the chemistry. I mean, the chemistry is very good, so it will be an improvement on the instrument. So now we try several techniques to measure like in dynamic mode and not in static mode. And some people or some paper publish data with a precision of 3 ppm. But today it's very difficult to be below this value. And we try several things. I think today it's not possible with the instrument we have.
And is this something that falls in the realm of what academics should be doing, or is it really a academic industry partnership?
Yeah, I think it's an academic industry partnership, and we try to work with the company. For example, here Thermo for the Triton, and I know that Dominic is doing the same with new instruments. So yeah, we try to work with them to improve the measurement and on several aspects of the instrument. So yeah, I think we will see in the few years. I'm pretty sure that we can improve the measurement. I mean, with only a few ppm, we will be able to see a very, very interesting signature. For example, in OIB.
Well, there is a question there from Val Philanson, who is saying, excellent talk. Thanks for sharing. And then she's asking, do your findings have any implication for the ongoing debate whether bull curves is or is not chondritic?
No, I don't think so. I think that we will have the answer coming from the chondrite, because now we start to better understand the nucleosynthetic anomalies and to try to define the origin of the Earth. And maybe what we need is to have more measurement on modern samples, because today we define the zero value with the measurement of the standard. And at the beginning, we work only on Archean sample to measure variation. And the question is, do we know where is the bulk Earth? Is it at zero, or we have maybe a very small difference? But it's always the same question of precision.
Yes, definitely. Michael was asking a question about what are prospects where we were making conversations, waiting for you. What are the prospects to find more samples that date from the first 150 million years of the Earth's history? Do you have any thoughts on that?
You mean to find new samples?
Yes.
Either from the moon or locations on the Earth.
New location on the Earth, I don't know. Maybe, but what is sure is that all these different locations, I mean, the terrain is very small. It's a few kilometers. So, for example, the Nouveau Agituk crystal belt has been discovered maybe 15 years ago. So it was a recent discovery. So probably, but I think that with the sample we have today, we can measure more samples. Because in fact, at the beginning, we select a few samples coming from the different cratons. And I think that now what we need is to have a very, a study focus on one location, and to show that the different systematic have been closed, or of the system have been opened during, because what we think we see with the Barberton chromatite is that in fact with the initial epsilon 143 neodymium, maybe okay we have this value, but maybe we can miss something before, and this can be seen only with the 142 neodymium.
Maud, I think we went through the question in the list. I have another question, which is, what is your take, and what can be done besides working on chondrites in identifying the hidden reservoir? What do you think about this?
I mean, I'm still working on chondrite, so in fact, today, I think that most of the deviation is coming close. So if we draw a line with the different chondrite, we see that the intercept is passing through the terrestrial value. But after that, we have still this uncertainty of minus plus 5 ppm. So it's still possible to have a small reservoir, but it has to be small. So, I mean, the difference can be a few, between 5 and 10 ppm in 142 neodymium. But today it's difficult to have the resolution to say if it's definitely chondritic or not. And that's why it will be important to have more measurement, I mean, more precise measurement of OIB samples to have an idea of the deep mantle.
To connect the stories, Maud, that you're telling us about the differentiation of the Earth to what seismologists can see and geodynamicists model, what are the prospects for putting constraints on the volume of these possible hidden reservoirs?
I mean, it's difficult to have to estimate a volume or a mass because it's always a combination between the fractionation and the volume. So we can play on these two parameters. But yeah, for sure, now we have very good resolution using the tomography. So this reservoir has to be small, of course. But I mean, I think it's still possible. If it's extremely enriched, it's still possible to have a small reservoir.
So something comparable in size to LLSVPs or ultra-low velocity zones, something in that order of magnitude.
Yeah.
LLSVPs are large.
They're a few percent of Earth's volume.
Yeah, they are large.
They're large with the right geometric projection. Okay, well,
Yeah,
our time is wrapping up. I think we only have 2 minutes left. So, Maud, I'm sorry that we had all these technical issues with the speed of the internet across the Atlantic Ocean. But I did want to thank you again for the inspiring talk.
Yeah, me too.
I did want to thank you for that inspiring talk and showing us how we can obtain new insights.
Go ahead.
So thank you, and I would like to thank you. It's very bad to be in my office today, to be alone, and to have to listen my presentation. And I would like to thank you for this award.
Yes. Well, the honor's all ours. So thanks again for the presentation and the discussion. And thank you, Dominique, for serving as a moderator. And congratulations again on the lectureship.
Thank you, Maud.
Thank you.
Oh, there she is.
Oh, there you are.
Good to see you. I will send you the questions. I copied them. And people have asked if they could see the video later, so you might have more questions.
Yeah, of course. I will be pleased to answer.
Yeah, I came into my office to make sure the internet connection is more reliable too. And to get away from all the construction and street noise and the leaf blowers.
I'm in my office, but... So thank you. Bye-bye.
Bye-bye, Maud. Take care, everyone, actually.
Yeah.
I don't know.
Thanks.
So I'm not sure what we do now, Dominique.
They should just close it. I don't know. I don't think we have control of this.